Good day to you all. In this part, we are going to discuss about the hardware software co-design. So each and every embedded system will be having an electronics which is going to have both your hardware as well as software. And in the design process, how this hardware software co-design takes place, right? Say for example, most of these arithmetic operations like addition, subtraction, multiplication, division can be implemented as a pure hardware. Right, say for example, there are different multiplier architectures are available, and there are plenty of half adder and full adder you might have studied. So pure hardware, these things can be designed, and these arithmetic operations can also be written as a software using some program. So what about the hardware and what about the software? Which parts can be implemented as a hardware and which part can be implemented as a software, right? And some part, what are the hardware requirements and what are the software requirements? And these two things can be simultaneously developed, and finally it can be integrated so that the development time of your embedded system will be decreasing or it will be optimum, right? So in this section, how I can design my hardware and the software simultaneously, that we are going to see now, right? So basically this is what actually we are going to discuss about. First we have to describe the process, right? That is called a system description. So what are the functionalities, what are the requirements and all those things. The second thing is, what is the hardware required, what is the software required, right? So we have to define, and what is the hardware requirements and what are the software requirements. Then we have to co-synthesize. So supposing if we are going to design a hardware, and what are the requirements for the hardware, how I have to design, how I have to interface, all those things should be done. And while in the software again, what should be the data size, what should be the memory size, and all those things need to be designed. Then we will start developing all the three. So there should be a software development team will be working on the software development, a hardware developing team will be working on the hardware development, and there should be an interfacing team which periodically monitors whether this software and whether this hardware is compatible to be connected together in order to achieve our final result. And then suppose if there are any changes are required, then we have to go for the hardware software partitioning again, right? So this is the basic flow chart that shows how the hardware software co-design is happening here. And we will see that in detail, of course. In the traditional embedded system development approach, the hardware software partitioning is done at an earlier stage. So that is actually the first part, you can say. Then, after that functional requirement collection, right, what are the requirements of the system, then we will be going for this hardware software co-design. And the engineers from the software group take care of the software, they will take care of the software development, right? What should be the architecture of that, or what should be the database, what should be the data size and all those parameters. And there will be a group of hardware engineers, they will be responsible for building the hardware required for the product. And there is a less interaction between these two teams, and the development happens either serially or parallel. Most probably, in order to reduce the time for marketing, that will be done parallelly. Right. Once the hardware and software are ready, the integration will be performed. These two things are connected together. The increasing competition in the commercial market and need to reduce time to market product. The product calls for a novel approach for embedded system design in which the hardware and software are co-developed. Simultaneously, they are developed. And then during the co-design process, the product requirements captured from the customer are converted into system level needs or processing. First we have to get the requirements of the customer. Then we have to list, right? So what are the characteristics or what are the needs of the particular embedded system? What are the requirements, right? Specifications. So all these things actually first should be documented. And at this point of time, it is not segregated whether it's a hardware requirement or software requirement. So we have collected what are the requirements from the user. Once this is done, the system level processing requirement and then transferred into functions which can be simulated and verified against the performance and the functionality. So we have to design a system, and we should be able to simulate and verify whether my system is working properly or not. It is actually the system level processing. Then the architecture design flow. So how I am going to do it? So the pattern of system level processing requirements into hardware and software that take place, right? So which part should be implemented in hardware, which part should be implemented in the software, that should happen, please. And each system level processing requirement is mapped as either as a hardware or software. Then the partitioning is performed based on the hardware software trade-offs, which is better. So that will be selected there. there are so many things. Say for example, there are some ready-made filter chips are there, filter models are there. Then again, there are some software models are also available. Whether my filter is going to be a hardware program or it's going to be a software that we have to design. Right. So again, the hardware software co-design will be useful in order to reduce the time to market process. That is what we have said. Right, fine. So we'll continue with this. The architectural design results in the detailed behavioral description of the hardware requirement and the definition of the software required for the hardware. Fine. The processing requirement behavior is usually captured using the computational models. And the models representing the software processing requirements are translated into firmware. Right. So whatever we call it's a software, when it comes to an embedded system, most probably it will be used as a firmware because often it won't get changed, but there will be some possibility of changing the firmware. So we can periodically update, like the operating system of your mobile phone, right? So whenever a new version is released, right, it may be an Android or whatever the version. So we have to periodically update the firmware, not necessarily daily or something like that, maybe in a year once or something like that, we can say. And the fundamental issues in the hardware software co-design are selecting the model, then I have to select the architecture, then select the language in which I have to code it, and partition the system requirement to hardware and the software. Right, on the right hand side you can see there's a diagram like system design inputs, right? So which we are having a design document where I have all the requirements and designs are consolidated from the customer. Then I have to do a yearly hardware software partition. So which is the software requirement, which is the hardware requirement, I will be doing it. In the software I will be starting my program. In the hardware I will start the modeling. Then simulation will be done in both the cases. Then the software and hardware will be implemented or will be made. And then finally we have to integrate the total system and we have to test this total system. And selecting the model. So first thing is how I am going to select a model. And in this case, a model is actually a formal system consisting of objects and composition rules. Right? It will be having some objects and there will be some rules. And it is hard to make a decision on which model should be followed. So there are plenty of models out there. Which model should be followed? Again, it's a tough decision, but according to our experience, we can go for any type of model like. And most often the designers switch between a variety of models from the requirement. So initially we will be starting with one model, and when the system is being designed based on the requirements, we can switch over to some other models too, right? Again, it depends. And the second case is selecting the architecture. A model only captures the system characteristics, right? It doesn't provide any how the system can be manufactured, right? So it gives, say for example, it is something like a flowchart, how it will be implemented. Now we have to do that. For that we need to select the architecture of the system. Now what should be the different architectures that can be useful for processing the data, right? So there are different architectures are there. One is actually the data path architecture, then complex instruction set computing, reduced instruction set computing, very long instruction word, single instruction multiple data, or multiple instruction multiple data, etc. So these are all different hardware architectures, we can say, that can be used in the embedded systems, and some of them fall into the application specific architectures, right? So it will be useful for only that particular application, and the other few are actually general purpose architectures, something like CISC or RISC. I think one example for RISC is our ARM Cortex M3 processor, which we have already discussed. And these can be used as a general purpose controller architecture. And there are some application specific architectures are also available, something like NOCs or ASIC or FPGA based designs. So all these things will become application specific cases. And this processor should have the capability of parallel processing classes, right? So something like VLIW, SIMD, MIMD, there will be some parallel processing is also possible here. This particular diagram, of course, gives an idea about this VLIW, stands for very long instruction word computing. And the very long instruction word computing is actually a collection of instructions, we can say, which will be processed using a register files, a set of register files, and which will be stored in the memory temporarily. And there will be some data manipulation device, something like loading for saving. There will be some hardware will be there. Then there is a floating point add unit, right, will be there. and then integer ALU may be there, right? Integer, now it can process only the integer data, right? ALU. Then the branching units, right? Controlling different locations, moving the control to different location, branching, that's called. So this is